Hey, welcome to this video on the implicit function theorem. The implicit function theorem is a way of working out the derivative of implicit functions, and it's a really helpful tool in economics, especially with applications like working out the tendency condition for budget constraint optimization. So yeah, in this video we're going to look at what the implicit function is and an example of calculating the derivative using it. Alright, so first of all, let's just have a quick discussion about what an explicit function is versus an implicit function. An explicit function is one that we're quite used to working with. It's a function where the dependent variable is explicitly expressed as a function of the independent variables, i.e. y is equal to f of x, where f of x is some function of x variables. For example, y is equal to x squared plus 2. And this is called explicit because we have an explicit relationship between y and x based off this function. Sometimes though, we only have information about the relationship between x and y based off an implicit function. And in this case, the dependent variable is mixed in with the independent variable. So we've got some function in terms of x and y, and that might be equal to a constant. The most classic example of this would be a circle, where x squared plus y squared is equal to 1. There's no direct rule where y is equal to blah 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 x. It's x squared plus y squared equal to 1, and any points that satisfy this equation give us a circle with radius 1. So if we wanted to calculate the derivative of a circle here, we can't use our standard calculus rules where we take the 2 to the front and then we get 2x, etc., etc., because those rules are for functions of this type, which are explicitly defined. And that is why we need a new theorem, a new rule, to calculate the derivatives of y with respect to x or vice versa in these scenarios. Okay, so another example would be this one here. Y to the power of 5 minus 5xy plus 4x squared is equal to 0. And this is describing the level curve for a bigger function here, which we can call g, and this is the level curve of 0, or the contour plot, whichever way you want to call it. And we cannot rearrange this to isolate y, and so we can't differentiate it using our standard derivative approach, and that is why we use the implicit function theorem. Okay, so the general idea of the implicit function theorem is given below here. There's 3 requirements you need to have satisfied. And if that's true, the derivative of dy and dx is equal to the partial derivative of that bigger function with respect to x divided by the partial derivative of the bigger function with respect to y, and a minus out the front. So too long didn't read, we've got this equation here, and we need to make sure when using the theorem that these 3 conditions are met. So let's talk about those 3 conditions. Okay, notice that there's also g here, which is talking about that higher order function. So if we were to look at, let's look at the circle. I feel like the circle is an easy example. This here, we could say, is a level curve of the function g of xy equal to x squared plus y squared. And when g of xy is equal to 1, we've got the level curve that is defined by this. And this here is our higher order function. And we need to make sure that this higher order function is continuously differentiable. And the way that this is written notation-wise is you have x0 is the input that generates the specific output y, and x and y collectively form all of the inputs of the higher order function. So in this case, there's no complex vector of inputs. The inputs are just x and y together here. So this is just x and y here. And we need to make sure that this is continuously differentiable around a neighborhood of all the points when this is set equal to 1. Okay, we need to make sure that it's equal to a constant. So in this case, the constant is some real number. And we can only apply the theorem when it is defined equal to a constant. So if it wasn't actually defined properly as a function, we wouldn't be able to use the implicit function theorem. And then lastly, we need the derivative of this higher order function with respect to y to not equal 0. that makes sense because we're dividing by this derivative, and if that's 0, that's going to break this equation because you can't divide by 0. Practically, that just means that you are having a derivative that goes off to infinity. But yeah, we can't calculate a derivative numerically if you're trying to divide by 0. So that's it. So those are the three things. One is that it's continuously differentiable in the neighborhood that you're looking at. Two is that you can fix it equal to a constant so that you actually get a defined level curve. And three, that the derivative with respect to the one that goes on the denominator is not 0. That's it. And then if you do that, you've got dy and dx is equal to the partial derivative with respect to x divided by the partial derivative with respect to y, the minus out the front. Okay, so let's use this theorem to work out, actually with the circle example, what the slope is. So yeah, let me grab some paper. If we started with this as a question, and we're trying to work out the derivative evaluated at the point 1 on root 2, 1 on root 2, then we can graph it like this, and the tangent line goes through this point here and just touches the circle, and effectively the derivative is the slope of the tangent line, and we're trying to calculate what that is. So using our implicit function theorem, we can define g as this function here. In this case, don't worry about the -1. We can make it simpler and just have the level curve fixed to 1. In some other contexts, people like to set it to 0, but don't worry about that for this. Okay, so our higher order function is x squared plus y squared. That means that our partial derivatives with respect to x and y are simply 2x and 2y. Okay, great. Evaluating it at the point of interest here gives us 2 on root 2 and 2 on root 2 for both x and y. And then we can now put that into our implicit function theorem because g is continuously differentiable. This is equal to 1. Sorry, I've just changed that on the fly, which is a constant, a real number. And the partial derivative is not 0 for gy. So that satisfies those three conditions, 1, 2, and 3. And that means the derivative with respect to, so dy on dx evaluated at this point is equal to this, and plugging all of that in gives us -1. And that's exactly what we'd expect just looking at this circle where we've got a straight line that is going with a slope of -1. That's actually visually quite obvious when you look at it like that. All right, that's an application of the implicit function theorem. And that also is the end of this video. I hope you found it helpful in working out how to use the implicit function theorem and how to understand, I guess, where it comes from as well. Thanks for watching this video.